All right, I want to talk about the RC circuit, which you are seeing in the lab that's due this week. And basically, this circuit consists of a capacitor, which is this element here, and a resistor, which is that element. And prior to the capacitor being in contact with the resistor and having its charge drain out, it has to accumulate charge. So initially, the capacitor is hooked up to the battery, which is right here. So the switch is initially in this position, and that it is at a certain time after the capacitor is at the same voltage as the battery, which happens really quickly, we flip the switch and we end up with this circuit, and the battery is effectively out of the circuit at that point. So we really just have the capacitor and the resistor. Okay, so what's going to happen there? Well, conceptually, you have charge on both plates of the capacitor, here and here, and that charge can't jump across the plates. That's not feasible. That would destroy the capacitor. But when there's a connection between the two plates, an electrical connection, the charge can flow through a circuit. That circuit could just be a wire, and you could get a spark across the two plates. Across the wire that connects the two plates of the capacitor. You could put a light bulb there, as you saw in the demonstration, and the LED or the light bulb could light up for a tiny bit. Or you could put a resistor here, and slowly the charge will drain out. The smaller the resistor is, the faster the charge is going to go through the resistor. All right, so that's conceptually what's happening. And as the charge goes through the resistor, there's going to be less charge on the plates of the capacitor. That charge is going to get diminished, and the voltage is going to go down. So somehow the voltage is going to go from whatever it is initially across the capacitor, and it's going to go down in some fashion. And we're going to try to figure out what fashion that is. That the voltage across the capacitor is going to decrease. All right, that's the voltage across the capacitor, which, as we're going to see in a moment, or as you probably can tell, is also going to be equal to the voltage across the resistor, because the two are in parallel. That's only those two elements, so they have to have the same voltage across them. Now, in order to do this problem, we are going to look at this equation, which we know it's the equation for the charge on the capacitor plates, and it's equal to the size of the capacitor times the voltage across the plates of the capacitor. That's the equation for the charge. We also have the equation for the voltage across the resistor, which is equal to the current through the resistor times the value of the resistance. That's Ohm's law, and we've talked about that earlier in the semester. So we're going to take those two equations and put them together, with the one caveat that I had already mentioned is that both of them have the same voltage across them. The voltage across the capacitor is equal to the voltage across the resistor. So I can set those two equal to each other and call them V. So I'm just going to say VC is equal to VR is equal to V. So I don't have to worry about, is this voltage a voltage across a resistor or a voltage across a capacitor? Then I can take my two equations, and since they just both have a V in them, I can substitute this V and its value into that equation. So my equation that I'm working with here is that the charge is equal across the capacitor is equal to the capacitance times I times R. Hopefully that makes sense, because this used to be a V. I just did a substitution. Now the question is, okay, that's a nice looking equation, I guess, but is there anything we can relate on the left side of the equation and on the right side of the equation? Well, for the purposes of this problem, R and C are both constants. R is the value of the resistance, remember, and C is the value of the capacitance. However, the Q, the charge on the capacitor, at any time is related to the current through the resistor. And I want you to think about it like this. You probably remember that this is the equation here for the definition of current. It's the charge moving past a point per unit time. That's basically the equation we're going to use. But the thing I want you to think about, I'm going to go back to this figure up here, is that as the charge moves from this plate, it's going to create a current. So as the charge decreases on the capacitor, the current is going to be actually positive. So this equation here is correct, except there needs to be a negative sign in there in this specific case, because the Q refers to the charge on the capacitor, and the I refers to the current flowing through the resistor. So in order to address the fact that as the charge on the capacitor decreases, the current through the resistor becomes positive, I'm going to put a negative sign in there. All right, so now what I'm going to do is I'm going to take this equation here. I'll rewrite it down below. It's this equation here. I'm going to rewrite it all the way down here. So I'm going to write, okay, Q is equal to C times I times R. I is negative dq dt. So this becomes what we know as a differential equation, where you have a quantity q that's related to some constants, which are these, times the derivative of that quantity q, and there's a negative sign in there too. So I'm going to rewrite this equation to accommodate what I just said. I'm going to say I'll put the RC over here. I'll put the negative sign. I'll put this negative sign right here. So it's Q is equal to negative R times C times dq dt. All right. Now, some of you have had differential equations, you might recognize this kind of equation, and has a certain solution to it. I'm going to go through it and we'll come up with a solution. But what I'm going to do is I'm going to get the q onto this side, and the dt I'll put over here. So I'm going to say, okay, dt equals minus r times c times dq over q. And what I'm going to do is I'm going to integrate both sides of my equation, knowing that these quantities here are constant. So I can pull them out of the integral, and what I'm going to get, the result is going to be, if I integrate dt, it's just simply t. That's pretty straightforward. On the right-hand side of the equation, I have minus rc times the integral of dq over q. And if you're